This is a continuation of Chapter 5. This is Chapter 5b, Clouds and Instability. And we left by talking about conditional instability, a situation which is a hybrid situation, but is actually more common in Earth's atmosphere more often than not, where the air is stable near the surface with respect to dry air, but then becomes unstable with respect to moist or wet air. So let's talk about, in general, the causes of instability. How can the air become more unstable, meaning that the parcels of air continue to rise on their own accord? This occurs when the air aloft becomes colder, or the surface air becomes warmer. Or you can actually have those two things going on simultaneously, which can really cause explosive instability if the air aloft is getting colder at the same time that the surface air is becoming warmer. This can really cause instability to get going. The cooling of the air aloft might be due to a number of things. If winds above our heads, winds aloft, bring in colder air, that's called cold advection. Or if clouds or the air emit infrared radiation into space, which causes radiational cooling aloft, that can make the air aloft get colder at the same time that maybe the surface air temperature doesn't change or gets warmer. The warming of the surface air might be due to a number of things, including simply the sun's heating the ground, i.e. daytime solar heating of the surface. Or if there's an influx of warmer air brought in by the wind, i.e. warm air comes in from someplace. That's called warm advection. Or if air warms up because it moves over a warmer surface. All these things can cause the warming of the surface air. So the cooling of the air aloft combined with the warming of the surface air can enhance instability. Another concept to discuss is that the mixing and lifting of air can cause instability. In the case on the left, figure 5.12, mixing tends to steepen the lapse rate, meaning that rising cooling air decreases the temperature aloft, and sinking warming air at the same time increases the temperature near the surface. So you can actually see a layer of air that is initially stable, but as the day progresses, warm air rises and cools, and then air aloft cools and sinks and air aloft that is cool sinks and becomes warmer, and this can take a layer of air that was initially stable and make it unstable. Or you can take an entire layer of air from the surface, which is relatively stable, and lift it. And as the layer of air is lifted, the entire layer is lifted, that tends to increase the instability of the layer. The initial stable layer, which is line XY on the graph on the right, because you can see the temperature is only slightly decreasing with altitude there, becomes conditionally unstable near the top, XY prime, Y prime, after lifting, because the air in the upper part of the layer is going to cool more rapidly because the air is less dense up there because there are fewer molecules per unit volume. When we talk about thunderstorms, we talk about something called convective instability. This is an instance where a very stable layer of air can be converted into an absolutely unstable layer when the lower portion is moist and the upper portion is quite dry. Remember that moist air is lighter than dry air, so it's going to want to rise much more rapidly than dry air will. So if you look at that initial layer AB, the temperature is actually increasing with altitude there. But if you take that whole layer of air and lift it, keeping in mind that the bottom part of the layer is saturated, very, very moist, relative humidity near at 100%, and you lift that entire layer up, all of a sudden A prime, B prime is in a situation where A prime is much warmer than B prime. So you have a much steeper lapse rate there. So when this entire layer rises, the upper dry portion is going to cool more quickly at the dry rate than the lower moist portion does at the moist rate. Because remember, the dry rate is 10 degrees Celsius per kilometer, and all the moist rates are going to be less than that. So the cooling is going to be much more rapid with the dry air and the wet air. The entire layer becomes absolutely unstable, and this can cause strong thunderstorms. Very common in the spring and early summer in the central and southern plains of the United States, which we will discuss in a future chapter. How do clouds develop? Well, we mentioned that clouds develop because air rises, expands, condenses as it cools. In other words, the lifting mechanism is strong enough so that the blob of air expands so that the temperature of that blob of air cools to the dew point. The temperature and dew point become the same, which means you have relative humidity of 100%, and voila, a cloud forms. There are 4 basic ways in which this can happen. If air from a heated surface rises, this is called the convection, or if air is lifted along a mountain barrier, along topography, this is often referred to as orographic lifting, example B. Or in example C, you have air streams that converge to a place on the surface and then rise, expand, and cool, and clouds form and showers develop. That's called convergence of air. This actually happens over Florida quite a lot. And then you have D, which is lifting along weather fronts, or frontal wedging, as it's often called. Basically, the warm, moist air, whether it's a warm front or cold front approaching, is forced to rise, which causes clouds and precipitation to form. So you have convection, which is just the heating of the surface. You have lifting along topography, which is just meaning that an air mass is slamming up against a mountain range and being forced to rise and then cools and condenses. You have convergence of air streams at the surface, or if you have lifting along weather fronts. This is how cloud development occurs. If you look at convection in clouds, here is an example, the graphic on the left, showing how a blob of air lifting from the surface is warm, and it starts to rise on its own accord. And then as it expands, as it goes up into the atmosphere, as pressure is lower up there, then it may cool to the dew point, and at a particular level in the atmosphere, a cloud may develop. This is called the condensation level. The picture at right is a perfect example of these rising blobs of air, which are called thermals, that reach the condensation level, the base of the cloud forms, and it causes the cumulus clouds to pop up like you see in the picture there. The clear areas between the clouds are regions where the air is actually sinking. More about clouds and stability. Now, the air stability, or lack thereof, greatly influences the growth of clouds of vertical development, which are cumulus clouds. If you have a situation where you have maybe some unstable air near the surface and the cloud forms, and then the air aloft warms up a little bit or levels off and becomes stable, all you get are what you see in graphic A there, just little cumulus clouds. In graphic B, you have a situation where you have conditionally unstable air in the middle levels of the atmosphere, and maybe those clouds will tend to tower a little bit, which means that way down on the surface the air is stable with respect to dry air, but then becomes somewhat unstable with respect to moist air. And of course, if you have conditional instability all the way up the column, as that temperature graph shows, then you have the potential for cumulonimbus, or thunderclouds, which have that classic anvil top up on the top. Let's talk a little bit more about mountain ranges, or topography and clouds. When a blob of air is forced to lift up along a topographic barrier, i.e. a mountain range, this is called orographic uplift. Now, there is a windward side of the mountain and a leeward side of the mountain. If you've been to Hawaii, you certainly know that. If you know that, if you've been to California, you know that too, because the windward sides get more precipitation and the leeward sides are dry. Windward side is the more moist side than compared to the leeward side, so that rising cooling air is on the windward side and sinking warming air is on the leeward side. Locations on the leeward side are dry locations, and this is called a rain shadow. This happens on the southwestern slopes of the mountains in Hawaii, and it also happens here in the western United States. The western slopes of the Coast Range are the windward side. The eastern slopes of the Coast Range, meaning the western San Joaquin Valley, is in a rain shadow, i.e. Coalinga gets less rain than Fresno does. Look at the Sierra Nevada. They're taller than the Coast Range. Places like North Fork get 3 times as much rain as Fresno because they're higher up. They're experiencing that orographic uplift. Meanwhile, on the other side of the mountain, the Owens Valley side, the leeward side, a place like Bishop, California, gets much less rain than Fresno does, so they are in what's called the rain shadow. Here is a little example from your textbook, Figure 5.21, showing how we start on the left-hand side of the mountain, which is the windward side, how temperature and dew point decrease with altitude, become the same as the cloud forms, and then when you get the blob of air outside of the cloud descending on the other side, you actually end up with a higher temperature and a lower dew point than you did when you started initially on the left-hand side or the windward side, assuming both sides are at the same elevation. Now, An interesting case is with lenticular clouds, which we discussed a little bit in Chapter 4. It's not always the case that airflow over a mountain range causes clouds on the windward side. If the air is stable and not excessively moist, and the moisture is in the upper atmosphere, then you can get these interesting wave clouds or lenticular clouds that form on the leeward side of the mountain, not on the windward side of the mountain. A rotor cloud can form on the leeward side, depicted in this graphic, figure 5.23, as the rising part of a swirling eddy condenses. This is very turbulent air and is an aircraft hazard. Now, one of the most famous photographs you'll find of lenticular clouds is a photograph taken by Ansel Adams in the early 1940s, which is called Moonrise, Hernandez, New Mexico. If you click on the hyperlink in this slide, it will take you to the San Francisco Museum of Modern Art and will take you to this dramatic photograph that I'm making reference to. So take the time to do that. This isn't just some dry ink in your textbook. You can see examples of these clouds in nature if you're an astute observer of the atmosphere. Although I will tell you that it's very difficult to see lenticular clouds from Fresno because of our air pollution here. They're much more vivid on the eastern side of the Sierra at places like Mammoth Mountain or Bishop. Then there's something called the lake effect snowstorm, where you get a big dump of snow on the leeward side of the Great Lakes. And here's how this works. In the fall and early winter, when you get the first cold, dry air masses moving across the Great Lakes before they get really cold, these air masses gain moisture rapidly as they race across the Great Lakes, because often the water temperature can be as much as 25 degrees Celsius warmer than the cold, dry air traveling over it. Therefore, on the leeward or eastern side or southeastern side of the lakes, you can get a tremendous dump of snow. These snowstorms are highly localized, and the graphic on the bottom shows you these infamous snow belts around the leeward side of the Great Lakes. For instance, Marquette, Michigan is a very snowy place. Buffalo, New York is a very snowy place, and so on, because of the lake effect snows. Whenever you see clouds changing form, then that indicates a change in the weather, perhaps a few hours or maybe a day or so away. Whenever you see these kinds of clouds, as shown in figure 5.25 in your book, altocumulus castellanus, that indicates that the middle levels of the atmosphere are becoming somewhat more unstable as tower-like extensions start to form and the clouds start to build up in the atmosphere. This could be a precursor to thunderstorms on a particular day. Now, maybe at nighttime it has rained and a cold front has gone through. And as soon as you wake up in the morning and the sun rises, you see that the sky is clear. It's sunny outside. You think, oh, what a nice day. You know, it's going to be a nice warm day. No clouds. Well, what can happen just an hour or two or maybe even a half an hour after sunrise if a moist layer of air still lingers on the surface after that nighttime rain with clear, stable air above? What you can get is enough daytime heating as the sun rises higher in the sky for parcels of air to rapidly rise, condense, and cool, with cumulus or stratocumulus clouds forming in kind of a layer. So even though the day may be initially clear, an hour or two later, if there was rain the night before, there could be a moist layer that you really can't have a visible manifestation of until the sun heats the ground, stratocumulus clouds form, and a clear morning an hour or two later becomes a partly cloudy or a cloudy morning. This ends PowerPoint Chapter 5b.